There you go.
There we go. Now I can share. And arrange this window so that there's nothing on your screen. Good. No gray boxes.
Just in my head.
Just in your head, you have gray boxes.
Totally. I just woke up at 5:40 a.m. and it's like, oh, how can we keep on sleeping? And it just didn't work.
Yeah, I heard it comes with age. Okay, shall we start, everybody? We'll continue with our circuits, but first, question. What are we going to ask you during the midterm? What are we going to ask? That's the question everybody wants to know, right?
So many questions, Look.
So I prepared a few slides with the questions from the midterm. And no. Basically everything here in this list. The way you should think about it is that everything that you have done, discussion and homework is now important, will be, that's a heck of a lot. That's true, Matt. But hey, this is Berkeley, and you have been here and you have been learning, and you should feel good about it. Look how much you have learned so far. Send this list to your parents, saying, look how much I learned in one class. Yeah.
I mean, what do you mean one class? I mean, we're just talking about what? Like
one class, 16A, 16A.
2 months, 2 months.
2 months.
One
exactly.
1.5 months, 1.5 months this time,
And then you can invite your parents to watch the search for the Holy Grail together.
Right.
You can say, I learned that too in class. Okay, and then you find out if they have a good sense of humor. Okay. All right. Are there questions on the topics of the midterm, or does it sound fair? You should recognize all the names there. This is the Minecraft, and yes. Okay. No questions.
Just one question.
About your Minecraft machine.
No, there's one question. One person who's raising their hands.
Oh, what's an NVA? NVA is the node voltage analysis that we have done last class. Okay, Ufoma, do you have a question?
Yeah, for like the concept of imaging labs, like, is it going to be like we have to like understand the concept of the lab?
Yeah.
Yeah, you'll have to know what you were doing in the lab. Why did your GSI say no circuits? Yeah, he's
made a mistake.
Yeah, it happens.
We apologize.
Yeah. Okay. Let's get started. Good moment to remember what we have done in the last lecture. So in the last lecture, which is in the midterm, Mom, do you have a question about the midterm before I start?
Yeah, on the Piazza post, it said we can use any like downloaded files. So can we like download all the notes if we want to?
Yeah.
Okay, thank you.
All right. So what did we do last lecture? Last lecture, we used 2 examples of circuits to do the analysis and the node voltage analysis for these 2 circuits. One was pretty simple, a resistor and a voltage source. And the other one was a special one, which we called voltage divider. I'll get to the voltage divider later. Then we did come up with a method to do the analysis of the circuit. And in this method, we were using linear algebra that we learned at the beginning of this class to solve the circuit. So what would we do there? We would come up with a matrix A that was describing the relationship between all the circuit elements. And we did that with several methods. One was using the definition of the elements, which we had wires, resistors, voltage source, open circuit. We used that definition to get some of the relationships, and this was the IV relationship. Or we use KVL or KCL to fill up our values. Then and come up with the equations. We had a vector x that was describing our variables, and our variables were all potentials and currents, right? And then we solved this to B, which were the values that we had for the independent currents and voltages, right? That's what we did. And you have that, and you have done that in the homework and also in discussion, and you will keep doing as we go. Okay, and then we looked at some special circuit, which will become very useful in this lecture and several lectures to come, which we called a voltage divider. And in that circuit, we had two resistors, R1, R2, and a voltage source that was giving us Vs. And then we did our analysis. We picked one node to be the reference. And then we had one potential here, U1, a second potential here, U2. How did we get that? By looking at the nodes, right? So here we have one, here we have another one, and the third. Does anybody remember the solution for U2, which was what we found out doing this analysis? You remember, Mickey? Good.
I do.
There. Other people don't remember. Huh. So it was a ratio, right? We found that. Oh, you have a voltage divider there, Mickey?
I do. And look, here's implementation.
Okay. Oh, good. Thank you.
Right, welcome. Ah,
It gets hot, right?
too hot. Yeah.
But you need to measure the voltage. Maybe later in the class, you can measure the voltage for us. Okay. So we found that U2, that potential was R2 over the ratios of the resistances, R1 plus R2 times Vs. Check the units, you need the Vs there. Very good. So we saw this was the solution that we found for U2. What does that mean? Well, we found a method that we could find an unknown potential, U2 in this case, using our linear algebra and all the rules that we learned so far for circuits. So we're going to put all these skills to use today, and we're going to do some more node voltage analysis, and we're going to start doing some design, because that's what we are here. We're learning skills and tools in math and in circuits to do design. All right. So first, a little bit of physics and the power, since we even had our nice music here. So how do we think about energy and power in circuits? This is pretty important because all the electronics that we carry around, we care about the power, right? We don't want to run out of power. So when you are designing these electronics, you need to care a lot about power consumption and power dissipation. So we have most of the concepts that we need to think about power and current in circuit and the energy in circuits.
You know,
we looked at current. Yes, Mickey?
You know, when we grew up, you know, computers were increasing in speed, but then pretty much you could at some point just heat, you know, water for coffee, on processors. And it was just like insane. And a lot of the revolution in the last decade or so, or maybe 2 decades, since phones started, is really the reduction of power in those chips. That makes a huge difference for mobile devices, huge.
Yes. But also the power consumption increased because of the number of devices increased.
I know,
So,
that's true.
yeah. It's a circle. It's a topic, basically. Okay, so last class we looked at current. What's current? The current is defined by the flow of charges that are going from a point A to a point B in a material, inside a material. That material, and for us, that material is inside our elements, and our elements can be a wire, a resistor, and others that we are going to define as the class moves on. So we define this flow of charges, and we could also write as an equation that's the flow of charges over time is our current. We defined that in previous classes. Now, energy, it does take energy to move these charges from point A to point B. So the energy that it takes to move the charges, what did we call? We defined this energy. Let me see the chat. Maybe Miki, you can read the chat for me.
Voltage.
Voltage. That's right.
No,
the energy
just
that
twice,
it takes.
just twice, not 3 times.
Oh, just twice. Oh,
Yep.
only twice? Not how many do we have here? 356
Just
times.
Andres and
The
Anthony.
energy
That's it.
to
Oh,
move
Lucas.
the charges
Go for
from
it.
point A to point B.
Everybody voltage. Come on.
That's right.
Yeah, there you go.
Voltage is
There you
voltage.
go.
And how did we define? So we said that the voltage to go from point A to point B is the energy that it takes to move charge. It's so difficult for me to write for you, Miki. Okay. Now,
folks, you have to appreciate Anna's trying not to write in cursive. So that's pretty incredible.
Because Miki cannot read cursive, but I only write in cursive. But I'll do my best. Okay, power. Now, what's power? Anybody?
Energy over time.
Energy over time. Yeah, that's correct. Energy over time. We can also say that power is the rate of energy, of changing energy. Ooh, almost in energy. So how would we write power? We would write that power is the rate of energy change. And we know that the energy change, the energy that we're consuming comes from moving charge. So we can actually use our definitions from previous classes to write that the power is going to be the energy that it takes to move charge times this flow of charges that we are seeing over time. And of course, this is our voltage definition. This is our current definition. So we can more simply write that power is voltage times current. Where units. Voltage we have in volts, current we have in amps, and power we will have in
What?
What? That's right.
What?
Okay. So far, so good. All right. Okay. So this is important concept because when we are designing our systems, we are looking at the voltages and the currents that our elements will have always a relationship between current and voltage. So, and that will translate into power. So, but just in space like this, just saying, okay, power equals voltage times current doesn't mean anything for us unless we apply to elements. So consider this a midterm review. So let's take an element. What do we do for the element here? Our element can be whatever, a box. The important thing is that we establish a current, which we call I element. And we say that there's going to be a voltage drop for these elements that we call the element, right? So if now we want to calculate the power for this element, we're going to say that the power of element, this is EL, okay, Mickey, is going to be the V element times the current flowing through the element. Sounds easy, sounds simple, we didn't do anything new. But now let's take some assumptions of different elements. Let's say that we have a resistor. So let's say if our element is a resistor. What happens? Let's apply the power relation here. We know that power is equal voltage times current. So in this case, if we have a resistor, power is going to be equal. What's voltage for a resistor? For a resistor, we apply Ohm's law, right? So we say that voltage is going to be equals resistance times I if we have a resistor here. So, okay, all right. For a resistor, power is going to be voltage times current, which means that the power is going to be the resistance of that element, I squared. Now here comes a very important definition, because we know that resistors are of a positive value nature. There is always a resistance. It can be very low resistance, but there's always a resistance. And here we have I squared. So we know that the power dissipated in a resistor is going to be positive. And in our passive sign convention, if you have power being positive, that means that power is dissipated. We are using the power in this case. Okay. There is one more way that you can show that that's true for a resistor. You apply the relationship, the voltage current relationship to the element. So, okay, I'll say V element is equal R times I element, right? Now, what's I element in this case? If it's a resistor, I element is going to be V element over R. So here, when we apply the power, now using the voltage, we say V times I, voltage times current. And then for this element, that's our resistor, we are going to have V element times V element over R. And again, we get a positive value, V element squared over R, okay? This is important. Resistors are consumers. They will consume power. So you have to think about your resistances as you pick your elements here. Okay, let's do other examples. We have more elements that we know. Are there questions so far, or so far so good?
There are a few questions about why is the power dissipated. Another question is about is really resistance always positive?
Really, yes. I hope I proved to you now. That would be always positive because we have the resistance here. And then if we have a squared, right, we are going to have a positive. Mathematically, we get a positive number there, correct? Mickey, you know math. You agree?
I do completely agree.
Okay.
So
All
'cause,
right.
I mean, if you're talking about experiences, the experiences may not be positive, but the power dissipated will be positive. For example, you remember what I did about the battery where you put a resistor? Yeah. You know,
Okay. Let's continue. Let's apply power. Power element equals V element times I element to other elements that we have. I'm going to pick now open circuit. Why? Oh, because we are going to use open circuit so much. It's just such a nice element that simplifies life of everybody doing circuit analysis. And that means you, my friends. Okay, so I have my I element. I have V element across the open circuit. So if I write for open circuit, power dissipated in this element is going to be the voltage of the element times the element. Now, memory, search your memory. By definition of an open circuit, what do we know? What do we know about the definition of open circuit? The IV relationship in an open circuit.
oh, so many good answers. So many good answers.
And anybody
equals
saying
zero.
that I equals zero? Very good. So if I have I equals zero, that means that the power dissipated in an open circuit is zero. Makes sense. There is no current going through it. Okay, another special element that we are going to use a lot today is the wire. So let's define here. I have I element. I have a voltage across this element, the element. What's going to be the power consumed by our element wire? And here we talk ideal case, ideal wire. What's the definition of a wire? IV relationship in the wire. Good answers? 369 of them? No?
No, only well, they say the voltage is zero. Oh, yeah, the voltage is zero. That's right. But it's just like 50, 50.
50?
Really, we need a little bit more participation here because it's like we want to see basically a Twitch channel of V equals zero,
Yes,
Twitch.
yes.
Yeah.
Okay. So power dissipated in these two elements will be zero. Power dissipated in the resistor is going to be substantial. Okay. I thought I had space to do one more here. Oh, I ran out of pages. No problem. I'll add a page here. Hold on. Add a page. Okay, let's do an example. And in this example, so slow example, I'm going to take a circuit and we are going to look at the power dissipated in the elements of every circuit. And that's also midterm review. Oh, such good class. Okay, so in this, let's do our good old circuit where we have a voltage source and the resistor. What did we do? Oh, before we freak out about any question that we may have, we centered ourselves and write the stuff that we know. Okay, I have VS and I have R. Oh, I'm going to look for the nodes. Okay, I go here, find another element. I go here, find another element. 2 nodes, great. Make one node the reference, 0, done. And then label the other node U1. Great. 2 nodes, 2 potentials. One is the reference. I know this is going to be simple. Now, let's define the voltages going through the element. So I have here voltage across this element, which I'll call V element. Let's see on my notes if I did element 1. Yeah, I did V element 1. Oh, and here, let's do something that circuit people love to do. Let's call this resistor a load. So I'm going to call this R load. And then say, okay, this is V going across the load. Basically, the load is what's consuming the power of this power source. But I'm going to show you this in this example. Okay, what do we do then? Let's do the analysis. So first, we do KCL. Oh, I didn't define the currents. Let's define the currents. Okay, I will put here current IS going in this direction.
Good choice.
And I'm going to use here current IL going through the load in this direction. Now we do KCL. It becomes more interesting, right? So if I do KCL, what does it say? It says, okay, the currents coming into the node have to be equal to the currents going out of the node. So this node here has one current coming out this way, another current coming out that way, nothing coming in. So I can safely write that IL times a plus IS equals 0. Yeah,
Beautiful.
I think so.
I think so.
Now
too.
let's apply. Huh?
I think so too.
Yeah. KVL. KVL. Oh, it's now when we have to take into consideration our potentials, our variables, and then measure the voltage across. So let's do this first for the load. So if I had to measure here the load, I go from positive to negative. So I will write U1 minus U0 equals the voltage across, which is VL. Okay, if I do for the other node, this node here, which is our power source, okay, I go from negative, positive to negative. So I will write that U1 minus 0 equals V element 1. Oh, but V element 1 is a special element. It's a voltage source. And because it's a voltage source, by definition, we know that V element 1 equals Vs. Good? So far, so good? Just applying what we learned in the last lectures. Okay, so now we want to do power analysis on our load, on our resistor. So we have power for the resistor is going to be power in the load. It's going to be voltage times current. And now because we applied already our rules, we can define a few things. So we can say that the power in the load is going to be minus IS. Oh, sorry. We made a small eraser here. Okay, we can say that the power here in the load is going to be minus IS times VL. Where did I get that from? Oh, from our first KCL here. Let me write here. I can say that the current going through the load is going to be equals minus IS because they were opposing in the node. Okay, now there are other things that we know. We know that we know what VL is. What is VL? Anybody? Any answers?
There's a few questions. VL,
We
U1,
did-
U1, U1, VS, VS, U1, U1, VS,
Yes, right? Okay, but let's go slowly. So we have
Well, I
VL
mean, they're
here.
writing so fast.
VL
What can I do? I mean, like,
I know they are good typers. Okay, we have VL equals U1. We have U1 equals V element 1, and we have V element 1 equals Vs. So all the voltages are the same, and they are Vs. Okay, so I will write like that, Vs. Okay, that's
So
an equation. Yes.
I know there was a question about actually doing the node, KCL on the other node. Does that make a difference or not?
If I were to do KCL here on the reference node,
Mhm.
I could, but because we use that node as a reference, right? Then that potential is no longer unknown. You can go ahead and do KCL. You're going to get more equations. So you're going to get redundant equations, but you can do, there's nothing that stops you from doing that. You just have to define the current. And we did that in the first class where we defined the current, but this element is a wire. And then because of the wire definition, we decided, okay, right? But you can do it. You're just going to get more equations in that case. But let's do the power analysis for the source. So for the voltage source. So if I were to write power for the voltage source that I have here, will be IS times V element 1. Okay, and by definition, we know that element 1, the voltage in element 1 is Vs. So here I have that the power of our voltage source is IS times Vs, while the power in the load is minus IS times Vs. So what did we find here? First of all, we found that the power dissipated in the load is equal minus the power produced by the source. Does that surprise you? Is that like a wow moment, or is like, oh yeah, that makes sense?
It's called.
Huh? Yes. What is this called, Mickey? Mickey, let the students talk. Okay, what is it called, everybody?
Can I read what they say? Can I read what they say, please?
One moment, while everybody's thinking, we define, I have to remind you here, that we define that the power dissipated in the resistor was always positive, right? Because our load here was a resistor. So, okay, Mickey.
They say conservation of energy. Woo!
Yes, conservation. I am
beautiful.
using energy here by writing this way.
And we're receiving it. We're receiving that energy, Anna.
Energy escaped. Okay, conservation of energy. This is such an important concept because you can actually check all of your designs by saying, wait a minute, is energy being conserved here? Sometimes you can check other people's idea and say, wait a minute, energy is not being conserved in this idea, okay? So a very good old concept that comes here in circuits too. Okay? Questions? Okay, then let's put our skills to work. Now, when I was here in the first class, I showed you how to measure voltage. Mickey is dying to show you how to measure things there. But how do we measure? How can we apply what we learned so far for our first design, very simple design experiment here, which is, how could we measure voltage or current? Let's start with voltage using the circuits that we know so far. So what I'll do here, I will really ask you to think, okay? And I'll give you time to come up with answers here. But the way I'm going to set up this design for us is that, okay, so I have a circuit and I want to measure the voltage going across the circuit, which I'm calling here V out, okay? Which is going to be our measurement, our voltage measurement. And then my question to you is, what needs to be in this voltmeter in order for us to measure the voltage across that circuit? So we can make a very simple model where we say, okay, I'm going to have a circuit here, a circuit that I know how to analyze. With a voltage source, I want to measure a voltage source that I don't know how much it's providing. I'll have a resistor. I'll have a voltage here that I'll call mystery. Which I will do some other handwriting, but I will always tell you, Mickey, that's the V mystery. Okay, and then right here, coming out of this circuit, I want to be measuring the voltage. So I will put 2 points here where we are going to have a voltage across, which I'll call V measurement. And then, of course, we have to build something that will allow us to measure this voltage. And that something is what I want you guys to think about, because you'll feel proud about yourselves.
Ooh, somebody
Okay.
said a good answer.
Oh yeah, but we are not
Yeah.
even there. I haven't even asked the question. Oh, they read the slides. Okay, so I haven't
That's people
finished.
who think ahead.
Yeah, like some of us. So I will define here. This is going to be V element 1. I need to define a current. This current here, I'm going to call I measurement. And then this voltage here is V measurement. This whole thing here, it's also inside of a box like we have there. First thing to consider, first of all, if I am measuring something, this measurement should not consume energy or change the energy in the overall circuit. Okay, that's a given. You can't interfere with your measurement. There was a famous person who studied that. So what is our goal here? What's our task? Our task is to find out what is V mystery. So our goal is to have V measurement being equal to V mystery.
Mm-hmm.
This is mystery, Mickey, okay? V measurement equals V mystery. Okay.
Love that name.
So how can we do this? We can apply the tools we have in hand, right? We are here in 3rd class of circuits in 16A. So let's do what we know. I can apply KVL. And if we apply KVL, what are we going to get? We're going to get that V mystery is going to be equal to V measurement plus V element 1. Makes sense? Let's look. If I'm going around the loop, right, then I know that the voltage have to sum around the loop. I defined my signs. So I have here positive to negative, positive to negative, negative to positive. So I know that V mystery is going to be the sum of V measurement plus V element 1. Element 1 is a resistor, so I can apply the element definition here, and I can say, okay, V mystery is going to be equal V measurement, which is my unknown, is what I want, plus V element 1. Since element 1 is a resistor, I can apply Ohm's law to it. And if I apply Ohm's law, what's the current going through V element 1? Well, the current going through element 1 is this I measurement, right? So by applying Ohm's law, I can write that V element 1 is I measurement times R. R, I know I picked that resistor. I am in charge of this design, right? Okay, so now, what's the only way that we can have V mystery be equal to V measurement? I know my
300
resistor.
answers. 300 answers. 300 answers. Come on. 1, 2, 3,
Come on,
4.
what's
5.
the only way that I can make V mystery in one side of the equation be equals to V measurement on the other side, knowing that resistor has a value?
Oh, wait, somebody says R equals 0. That's a problem.
Yeah,
Somebody says I equals 0.
I equals 0. That's it.
And somebody says open circuit. Something R is
Okay.
infinite. There's all sorts of answers here. All sorts of answers.
All sorts.
So-
Well, the answer I was looking for, 365 answers, was only this term can only be 0 if I measurement equals 0, because the resistor has a value that we know, right?
Yep.
Okay,
And that's most of the answers. Most of the answers.
and that's most of the answers, of course.
Yeah.
Okay.
I think it was 150 only though.
Okay, now some people cannot type, or they're that fast, or they are doing something else. V measurement. Okay, so we can say here, okay, only if I measurement, I need to move, otherwise it doesn't let me write here, equals 0. Okay, that's the only way that this circuit, we can do this measurement. Now I ask you, how does this circuit, our measurement circuit, has to behave then in order for our current to be equal 0, our I measurements to be equal 0? What behavior are we looking for here? What element do you know that by definition current is 0?
Yeah,
Yes?
no, the people are answering. It's like it starts with an
Yes.
O, ends with a T.
It starts with an O and ends with a T. Okay.
And then in the middle, there's a space.
So did our amazing students say that our measurement circuit needs to behave as an open circuit? Did you ever think that such a, open circuit could be so useful? Nice, right? It has to behave like that. In reality, we have many, many elements, but the outcome of that circuit behaves like an open circuit, does not interfere with the measurement. If I had to say, okay, I said here, energy cannot change. So if I say power, voltage times current, if we guarantee that behaves like an open circuit, the current then will go to 0. And if the current goes to 0, our measurement setup is not consuming power, not changing the energy of the setup. Very good, very good. Do you want to measure anything, Nikki? Or should
Sure.
I keep going?
Let's what do we want to measure? I got this battery.
Voltage.
Let's
You
measure
have to
voltage.
measure
All right.
voltage. Yeah.
All right.
Meanwhile,
So-
I'm going to set up the design for current, okay?
1.5 volt battery. Let's
slow
see.
in drawing.
Wait, I need to hold it. Hold on. 1.5 volt battery. Pretty good. Looks like 1.5
Very
volt.
good.
You know what's gonna happen if I put the red at the back and the black at the other side? Ooh, Negative, that's right. Okay, now I'm gonna take a 9-volt battery. 9-volt battery.
I'm almost ready.
Okay, I'm almost done. 9-volt battery. Ooh, this battery is no good. So it's not a 9-volt battery anymore.
Oh, I have a good one here. Do you want it?
Need to charge it.
Okay, I'm ready. Very good. So now, second design. Second design on your pocket, okay? Similar problem, but now what we want is to measure current. So what I set up here, I set up my circuit that's going to be my model or our model. We're doing this together, we are in this together, where I have a supply of currents that I'm going to call, oh, sometimes this thing doesn't let me, right? Mystery, mystery, which is being supplied. And then with this outside circuit here that we are going to decide how it's going to look like, we are going to measure current. What did we learn? We learned that that measurement, that setup that I have here cannot consume or change the energy. So we have to think carefully about our setup. We have a current, we have a load here, resistance. And now let's write all the currents that we have here. Of course, I have I mystery. And then over here, we're going to have a current going through the resistor, which I'm going to call IR. And then going out of this load here, of this node, I will have my I measurement, which is the current that we want to measure. We know that there will be a voltage drop here, which I will call V measurement, like we did in the last setup. That's it, right? Now, let's do our assumptions. Our goal is to measure I mystery. Now, if we do now KCL, because we are dealing with currents, so if I do KCL, what can I write here? What's the relationship between I mystery and the other currents in our setup? Did we get good answers? Okay,
It
the
says
answer
I
is
mystery equal to I measure plus IR, I mystery.
yeah, very good. And this is simple, right? We get this node here. We have I mystery coming in. We have IR coming out, I measurement going out. We apply KCL, we learned, we remember, and that's what we write. Now, we want to measure I mystery. So in order to measure I mystery, we have to come up to a situation where I mystery is equal I measurement. And what's the only way that we can get this to be true?
All right. Ooh, R equals 0, IR equals 0. Yes,
That's correct.
I know. Yeah,
If
that's right.
IR,
IR equals 0, IR equals 0, IR equals 0, IR equals 0.
yes, we are learning.
Really?
Okay, so if IR equals 0, that means that we can say I mystery equals I measurement. Now comes the question where you go and get all the knowledge that you accumulated so far from this class, and you tell me, IR, I'll tell you, IR is V measurement over R, right? Because it's a resistor, we apply Ohm's law, we write the voltage current relationship for that element. Now, what's the only way that we can get IR to be 0? We know resistor
R equals infinity, R equals infinity, R equals infinity.
Or V equals 0. So if we have V measurement equals 0, IR will be 0, which means that we have I mystery equals I measurement. what element do you know that we can apply V equals 0? That we can say for sure that that element will be V equals 0. Mickey, you're a very good student. Do we have good answers?
Yeah, why? By the way, great
Fantastic.
show. Great show, by the way, The Wire.
Wire. Okay, so that's it. You see, we're very, we played with 5 elements and we could come up with a design. So how are you going to measure current? To measure current is slightly more involved than voltage, because now we need this circuit here to behave like a wire. And you can see that the current has to go through this wire in order for us to measure it. So you have to place your ammeter in a position of your circuit that your ammeter will behave like a wire, allowing the current to go through it. And that's how you are going to measure it. Okay, you're going to, oh, you are measuring it. Very good. Thank you, Mickey.
So we measure 1.5 milliamps with 1.5 volt battery.
Now, let's keep designing. All good? No questions? All right. We have more designs to do. And now that makes my heart go a little bit faster because it involves materials and I love materials. Okay, so last class I stopped here where we were talking about resistors and how resistors were in reality. And the resistors are made of materials, conductors that are not ideal. And we stopped our discussion right here where we were talking about the resistivity of a material, the electrical resistance of a material, and the conductivity of the material, which are the 2 jargons that people use to refer to how good a conductor is or not. So today, we are going to use our intuition that we have for resistance and come up with a relationship that will give you a relation between resistance and properties of the material. So first, we consider a wire, a resistor, such that we have here. Adita, do you have a question about this?
I actually had a question about the previous slide in which you added a wire in parallel to the resistor. So why does that not short circuit? Because if you had like a voltage source instead of a current source, that would just mean that the current would pick the wire every time because it always flows in the direction of the lowest resistance. So like, does the current source somehow regulate the amount of charge that is generated, or does something like that happen?
No, you are right. The way you're thinking is a little bit ahead of where we are here in class. But if I say this is a short circuit, it's essentially the same thing, right? How do you create a short circuit? You put a wire through it.
Yeah.
So you're right. And this simple explanation here is also right. Okay, thank you. All right. So resistors. So resistors are made of materials, wires. So what we are considering here is that we have a conductor, a real conductor. And we know that a real conductor, when you make this real conductor into a resistor, it will have some sort of geometry. It will be more like a rectangle that is forming all these resistors that Mickey is holding. They're blocks, right? And they are formed from different materials. Now, if we have current going through here, this resistor, we know that because we have materials here, these materials are going to oppose the flow of current. So what's the flow of current here? Charges that want to pass through these materials. Well, as the charges try to pass through these materials, the charges meet other atoms that are forming that resistor. There are collisions. Collisions slow down the flow, right? And that's really the physical interpretation of resistance. So let's take a look of how these geometrical values here of a resistor could influence the resistance. And that's where I want to arrive at a relationship between resistance and property of the materials. So let's assume first that the wire, we change the length of this wire. So if I change the length of the wire, I go from a short wire to a longer wire. Am I going to increase the resistance to current flow, or am I going to reduce? If these charges are passing through a material and I make that material longer, what happens to the resistance?
People say something with I and ends with an E.
Oh, good. It will increase, right? So I can say that the resistance of a wire, a film, or a non-ideal conductor is proportional to its length. Now, so the longer the wire, the more energy is lost. Oh,
You know, I have
what
this,
that means?
I always think about it also as, you know, like you're going through like a bush, like a bushy area. It's very narrow and you kind of like, I have to go through, I have to go through this. Like I need to get to the other side. And if it's just longer, it's just more resistance.
It's just like picking tomatoes in my house.
Oh yeah,
Right?
totally. Yep.
Hard.
But
Yeah. Okay, now let's look at the other geometrical part here, which is how wide this wire is. So let's say I go from a skinny wire to a wide wire. What's going to happen to the resistance? Does it start with an L and ends with an R?
yeah, it's well, it's sometimes it starts with an L and also ends with a question mark.
Oh,
But,
okay.
but before the question mark, it was a S. Yeah.
All right. Okay.
Less,
So
less,
this
decrease, less.
very good. So once we make our wire wider, we are essentially changing this area here, which we call cross-sectional area. Okay, please use those smart words when you talk about it. Cross-sectional area. So the resistance is inversely proportional to the cross-sectional area. And then there is something missing here, which is a constant that is a characteristic of the material, which we'll call rho, which is this values here that I gave you last class. Okay, so the wire properties depend on the material's choice. You have choices, right? And now we saw that the resistance is going to change the power consumption too. So, you know, connect the wires here, connecting the dots. Okay, so let's do our touch screen experiment that you're going to do in the lab when you return to the lab. The second lab is resistive. Well, you're going to do both resistance and capacitive touch screens. Touch screens, we all know, right? We are familiar with touch screens. We press on them and they do stuff for you. Cell phones, everything. Children today, if they go to places that is displaying some information, sometimes even a picture, they will try to press on it, little children. That's what we're going to study here, the resistive touch screen. in reality, touch screens, a lot of them are capacitive, not resistive, but there are some that are resistive. So when you touch on something and it's squishy, that's resistive. And when you have a touch screen that is hard, like the ones on the cell phone, that's capacitive. Okay, that's the way to say. Why? Because resistive touch screen rely on the deformation of a material in order to provide contact with a different material. Typically, these touch screens are have some sort of a conductor that has been deposited on a flexible film, and it needs to be flexible because you're counting on the deformation of these materials to make contact with another material, another conductor that is down here. And once you have a contact here, you have a short circuit, you have a wire essentially connecting them, okay? So typical materials, ITO, what's ITO? That's Indian tin oxide. It's a transparent conductor. And it's used in almost all of our screens. Even the screens that you're watching this now has ITO in it. I have some examples here of flexible conductors. This is a flexible solar cell. This flexible solar cell,
we
you
can't see it. No, it's like your Zoom thing. Zoom does signal processing on this, ruining the electronics.
Oh, no, it's not going to ruin anymore. Check this out. Okay, this is a solar cell, and flexible solar cell, slightly transparent. It has conductors, it has metals. Can you see the metal lines here, metal grids? And on this side, where the light comes from, it's transparent. That's ITO, some sort of flexible conductor. I have our favorite flexible conductor here, Mickey, our MRI coils. This, this is printed silver, which Mickey and I did quite a bit of studies on. And of course, in your hands, you also have a flexible conductor. If you go to your kit and you see this part of your touch screen, this is printed also, and this is carbon ink. Okay, so you see it's on a flexible substrate, and you can go and measure the conductivity. You can measure the resistance across in these wires. Okay, so a little bit of materials for you because you know, we need materials. Okay, so here in this plot, I'm just showing you how when people are developing the materials, what they look for in the materials. So they can look at, here is transmittance. I'm sorry, this is covering. And here is sheet resistance. I will talk about sheet resistance later, but it's a geometrical assumption of resistors and how transparent that needs to be for the different applications like photovoltaics, solar cells, or screens like the ones we have in the computer. And here it is, capacitive and resistive touch. What do we learn for this? Actually, the resistance can be quite high. Doesn't need to be very conductive. That means the currents are going to be pretty low. While on the solar cell, which is a current source, we are generating current, the resistance needs to be quite low, okay? So we will do our first design, our third design of the day. Come up with a model to explain touch screens, where we have in the touch screen, we have a mechanical action that is that we want to explain electrically. So our problem, what our boss told us to do is to find out. So let's say here the problem. We always define. We always start to design with the problem definition. And the problem is to find to find the location of touch in this touch screen. Okay. How do I do that? Well, I have to go from this mechanical action to an electrical quantity. So how do I go from mechanical to electrical? Well, I come up with a circuit model, which is what we have been doing on the entire class, right?
Wow.
Cool. What do I
That's
have
amazing.
here? I think so.
Oh, tell us more. Tell us more.
I will. So what do I have here? I have a conductor, a flexible conductor at the top. I have another conductor at the bottom, which I'll call top plane and the back plane. And what I want to measure is this distance L touch. So first thing I'm going to define are the distances, which are L touch, where I'm touching here on the screen. Then I have L rest. The rest doesn't matter for me because all I want is to measure this point here of touch with reference to the total, which we are calling the length of this film or the length of your resistors here. Okay, so let's, yeah.
What parameters do we know and what do we don't know in this? That's a question about that.
What do we know? I'll get there. If you wait, I'm going to put all the parameters here. But what do we know? So far, you can assume only what I told you, which is there is a flexible conductor at the top. There is another conductor at the bottom. We press it and we get a signal. And we want to find out what's that signal and where are we pressing. Good enough?
Do we know
For
the
now.
width and do we know the width and all that stuff?
Do we
Or
know?
we don't
Yeah.
care?
Oh, we care. And it will come up in our model because it's going to be a pretty good model. Okay, first model. First model, I'm just going to take this top plane and be realistic and say, okay, I have this conductor and I know that this conductor is not very good. I even showed you the plot saying that it's not really a perfect wire, right? It's not a very good conductor. I know what I want. I want L touch. I know the length, that's a known, and I know what's left. Well, I'll find out what's left because I'm going to find out L touch. So the first thing I'm going to do is to build a circuit to describe this problem. So you see here in the drawing, I already attached, this is from your notes, by the way, you should read the notes. I attached the voltage source for this. I'm going to say, well, since I know that this material, this red film here is not a perfect conductor, not perfect conductors behave as resistors. So I'm going to call that first length that I have there of resistor 2, and I'm going to call this other resistor here, the remaining of the length of the conductor, resistor 1. Now I'm going to write the circuit here. I will draw the circuit because I got used to analyzing circuits now. It makes life so easy. Everything is more simpler this way. Okay.
Isn't it funny that using capacitive touch to describe resistive touch?
It is funny, right? Yeah, I'm doing capacitive touch here while I draw the resistors. Okay, so I have my power source, resistor 2, which is the length L touch, resistor 1, which is the length L rest. What do I have to do? We are new to this, so let's look at our nodes. Okay, we have one node here, we have one node here, we have one node there. Okay, next I need to choose a reference. I'm going to choose this node as my reference. Then I have to name things. I know that in this node, I'll have a potential, which I'm going to call the potential in the middle, which is U mid, which is what I want to find out. So our model is resistor 2, which is the length that we want to find out, and resistor 1, which is the remainder. Now, if I don't know the materials, what am I going to say? I'm going to say, okay, resistor 1 is going to be rho times the length, which I called L rest, over the area. Resistor 2 is going to be rho, property of that material. In this case, they are the same, times the length of that resistor, which we are calling L touch, our unknown, over area. So we have two equations and we have a circuit. Okay, is this circuit difficult to solve for you? Wait a minute, doesn't it look a little familiar? When you have a voltage source, two resistors like this,
All right,
and
all
I
right.
want to know.
Everybody, come on, do it.
Right?
Yeah.
Oh my gosh, we can use
Not
what
fast
we
enough,
learned
not
for
fast
something
enough.
useful.
Ew.
Yeah?
There you
So,
go, there you go.
okay, tell me, Miki, what is humid?
Starts with a V, ends with an R, space in between.
Very good. Well, this is our voltage divider, right? It's the exact same circuit. Convenient model. And you know what? That's what engineers and physicists like, convenient models to explain. Okay, so we know actually the solution. We can just write that the solution will be R2 over R1 plus R2, the ratios, times Vs, which was the result from our voltage divider. But now we got a little bit more sophisticated in the definitions of resistance, and we know that resistance are made of materials. So we can write R2 as the relationship for the material and the length, which is our unknown. So we are going to say R2 is rho L touch over area. Then we will have R1 rho L rest over area plus R2 rho L touch over area. Well, now what happens here? All the resistance values go away, all the areas go away, and we are left with a relationship between potential and length, which is exactly, okay, sorry, I forgot Vs. This would be not correct without Vs. Okay, so now we have a relationship between potential and length, which was part of our problem. So we can write that humid is going to be equal the ratio between L touch over L rest plus L touch times Vs. Okay.
You know, Anna,
Yep.
I was thinking, you know, it's good that Volt, his name was not Bolt, you know?
Right.
If
Why?
his name was Bolt, then voltage sources would have been just, you know,
BS.
BS.
Yeah. Sometimes your mind brings us so much enjoyment. Okay, so L rest plus L touch is the total length of the wire that we defined right here, right? So I just rewrote here, short, humid is equal L touch over L. That means with this nice, powerful little circuit that we have here, we can always get the voltage between these two resistors. And we can find out L touch, which is our unknown, if we know the length of the resistor, which we know, right? We are going to design something we can measure. Okay. We are going to come up with other models. Oh, we have 5 minutes, I'll keep going. So let's do a more realistic model because I took a shortcut here. And the shortcut was I took only the top plate, right? I ignored
Mm.
the bottom plate.
Mm.
Because I really wanted to use the voltage divider because why not, right?
Right.
Okay, now let's take into account the other plate. Okay, and we know that the other plate is also, in reality, it's not an ideal wire. But for our second model here, so I'm just going to write here, model 0. We found out that umid equals R2 over R1 plus R2. Yes. Okay, just so it's there for when we need. Now, our second model, I'm going to say, let's consider that bottom plate as an ideal conductor. And let's say an ideal conductor could be an ideal wire. Okay, and that's how we are going to make the circuit. We have the top plate, which we already considered the top plate and have a nice working model for the top plate. That is our voltage divider with R1 and R2. And now here I'm going to want to draw this as a wire. How would that look like? Okay, let's do our circuit. So first,
I like where you're going.
You like where I'm going?
Oh yeah.
R2, R1.
Guess what? They're going to do that in the lab, huh?
Yeah, isn't that cool?
They're gonna.
Our
They're gonna do it.
students are really lucky. Okay, where am I going to put this wire? Well, I have right here, umid is where we are touching. And then I'm going to say, and then this part, as I press, I'm going to make contact with an ideal wire that we put there. So I'll put it like this. So far, so good? Okay, so by doing so, to our nice little voltage divider circuit, we added some elements. I'm going to label our nodes. We had this as the reference. We had this as umid. Okay, and now I want to see everybody answering. What are the elements that I added to our new model? First one, obvious, the wire, right? So we have element 1, which is a wire, which we added here. So where is our wire? Our wire is, let me use the laser. Our wire is right here. We added the wire here. That's one element. Element 1 is a wire. Okay, what are the other elements? Any question, any answers, Miki?
Open circuit, open circuit, open circuit. 2 open circuits. Open circuit,
students,
question mark.
yes, these students are in a row. We added 2 open circuits to our system here, to our model. Now I'm going to say element 2 is an open circuit. Open circuit. What do we know about open circuits?
What do we know about open circuit?
Yeah.
I equals 0. Current equals 0.
Current
I equals 0. I
equals
equals 0. I equals 0. I equals 0. I equals 0.
That's right. Very good. Very good. So let me do the definitions because you know you do have this in the midterm. So we have V element 2 here, and we have V element 3 here, and we are going to just do KCL to solve this. I can keep going. 1 minute. 1 minute. I will just set up the equations because then you can keep thinking about it. Okay. So here I just copied everything we needed, and let's do the definitions from our elements. So for element 2, what can I write? I can write that V element 2 is going to be equal the definition, right? We apply the difference in the nodes. So I have 0 and 1 here through the open circuit. So I'll say U1 minus 0. That's the definition of our open circuit. For element 1, which is our wire, we are going to say V element 1 is equal U mid minus U1. Where am I getting this from? Oh, I have U mid here and U1, and this is my wire. So definition of voltage, the difference in potential. And then for E elements, okay, I'm going to ignore element 3 for now. Then we apply KVL, all the voltages. So if we go through the loop, we are going to find that U mid minus 0 is equal to V element 2 plus V element 1, where element 2 is our open circuit here, and element 1 is our wire. And what am I doing? If you go through the loop, you also find this, right? And if you remember, the definition is going from one place to the other. So if I go from minus to plus, and I have that this is U mid, where the potential I'm getting to, I'm getting there through V element 1 and through V element 2, okay? You get 2 lifts to go to the top. Okay, unfortunately, we have to stop here, but I'll pick up and finish our model in the next class.
Well, it's like, you stop it, it's like a, how do you call it? A cliffhanger. It's the cliffhanger.
It's like, da-da-da-dum. What
Da-da.
comes the next class? It's
Next
going to
time
be
on EECS 16A.
on Thursday. Okay. Kiddos, have a good day. Be good people out there.
Bye. Thank you.
Stay safe.
Thank you.
Bye.
Sleep.
Sleep always,
Important.
always. And study. Study
Important.
hard.
Study hard.
All right.
Say no to. Bye, everyone.
Okay.
Do we record? Oh yeah, we're recorded, right? Yeah.
We were recording.